Okay. Um, okay. First of all, we'll talk about retaining walls. So the main program we've got is Frew, which is our cantilever or embedded retaining wall program. I'm also showing Starball here. Up until quite recently, we had two separate retaining wall programs, Frew and Starball, both dealing with similar related problems. One was stability, one was overall analysis. We've now combined these two into the one program. So we now just have Frew, and so Frew does both stability checks on the wall, and it does the whole construction stage analysis for deflections and beam modes and so on. And it is suitable for any type of embedded or propped retaining wall problem. The way it works is that the wall is modeled as a series of finite element and beam elements running between a series of nodes. These nodes are then connected by Winkler springs into the saw model. The saw model is actually a finite element mesh, and when you specify by your dimensions, when you're putting in boundaries and rigid boundaries and so on, these are actually defining the limits of the finite element model. Unlike previous versions of Frew, if you use the early versions of Frew, where there you had to specify all the locations by nodes, we're now doing all data entry by level, much more directly, because now we have automatic node creation. We've got new dialogues. This is coming from the stability check within the stability check which came from Starball and is now included in Frew. And unlike previously, if you did the Starball stability check, you'd had to do one check for every construction stage, whereas now Frew will do a stability check for every single construction stage, and as part of that, it will then work out your required toe depth embedments for every stage, and then give you the worst case. We also have Eurocode and other design partial factors in there. So if you're working the Eurocodes, we have a number of design options in there. So you can be Eurocode compliant. You can of course set your own as well if your particular design code isn't included. So let's have a look at an example. With Frew, as I mentioned, it is a multi-staged analysis, and what we have in Frew is the initial stage, and where we define the various soil zones, and then as we add in additional stages, we then start to add in the wall, make excavations, add surface loads. We might add in struts, props, anchors. These are all defined in this strut table, and we'll define which stage they go in, which stage they come out, if at all. Their pre-stress and stiffness. They can be at an angle or have a lever arm as well. So you can define them quite well. And in this particular example, we've got multi-stage excavations, another prop going in, some construction load at the base, dewatering, change the pressures, changing the soil parameters, and so on. Initial moving plant loading, and then finally wall and strut relaxation for the long-term behavior of the wall. Now the wall itself is defined in terms of stiffness. Now we can vary this stiffness between stages. For example, you could reduce the EI value to allow for corrosion in the long-term behavior. You can vary the stiffness of the wall, maybe to allow for changes in the wall, or again corrosion or that sort of thing. Now, to create the nodes, we now have the node generation data dialog. Let me just close out some of these modes. And if you want, you can specify the nodes manually as before. But I'm going to do it automatically. So for an automatic node generation, we can then do a stability check. So this brings up the starball checks, and you see each of these is either free earth or a fixed earth check, depending on whether there are props present or not. I'll just run that, and you see it's run through all the various stages, and it's given us the various toe depths we require, and that's now shown up here. So the lowest toe depth, 37.34. I'm going to round that down to 37 meters. Once we have that, we can then generate the nodes, and you see Frew has calculated where all the nodes are required to be based on the soil levels, the strut levels, and so on. Okay. With all this set in motion, what we can now do is analyze this model. And as part of the output, we get we could get information for every single stage. If I go down to the bottom, we also could get some envelope results. So we get a tabular output of all our results, and we also get a graphical output of, say, the pressures, the bending moments, deflections, and shear forces. And this is at every stage through the construction. Or of course, we also get to the envelope, which is the worst positive and negative values of each of these, which we can then use for design, and we can check, and we can say, okay, the displacement is about 60 mil, 80 mil, whether that's acceptable or not, and the bending moments, and so on. So, in summary, Frew it analyzes the wall and the ground throughout the construction, from the initial conditions, the installation, the excavation, and into the final condition for wall relaxation and corrosion. And it's looking at the horizontal equilibrium of the whole model, fixed earth and free earth checks, and also sort of the ongoing horizontal analysis options in there as well. Now, I mentioned that Frew requires an EI value. You can count this by hand, but if you're dealing with a concrete wall, then our program Adsec is ideal for this. Adsec is a non-linear concrete and composite design program. It's used a lot in for piling and retaining walls. It can deal with straightforward reinforced concrete. It can also deal with composite sections. So if you've got a king post wall, and similar types of constructions, you can model that in Adsec, or even more complicated sections such as that bridge beam over there on the right. What Adsec will give you is section capacities for your reinforcement and so on. This is axial moment charts, gives you moment charts for various axial loads, and it gives you the section stiffnesses as well, which you can then feed back into Frew. We have a wide number of design codes: European, American, Australian, Hong Kong, British, and Indian. We've recently added in additional Australian and American and Euro codes, and part of the Euro codes, for example, you can now do concrete cracking to Euro codes. So let's have a look at how you do a diaphragm wall in Adsec. I'll specify my code, and I'll do it as a wall, so this to be a section out of a longer wall. I'll call it diaphragm wall. I can set my concrete grade. Could also set other things such as steel and FRP. I'll go for concrete at the moment. and I'll set rectangular section. That's going to be 600 deep and a nominal meter wide. Aggregate size, which can affect the concrete strength and detailing. And then template reinforcements. If I just have 2 lines of reinforcement on either side, so first of all I'll set the cover. Now we do have cover codes for various exposure classes. In our particular case, as we're casting up against the ground, I'll put in the usual 3-inch cover. So top and bottom reinforcements, bar spacings and diameters. I'll do the same on both sides. We can also add in individual bars. We can pre-stress bars, individual bars, lines, arcs, and so on. So we can get quite complex. If you want to add in divvy-dag bars or other sort of special bars into the section, you can do that. So there we have our section. Now, from this point, as I mentioned, we can just get our axial moment capacity charts, and we can see for 0 axial load we've got moment capacity of about 1500. Okay, I may have put a bit too much reinforcement in for that particular wall, but it gives you the idea of how it works. And likewise we can get the stiffness out, and you see for a given axial load, which is 0 in this case, it's a retaining wall, you can read off the moments and then find the cracked section stiffness. So you can see here the concrete is cracking at this point, and then in the reinforcement is beginning to yield and takes up the load until it finally fails over here. This EI says that you can pass back into Frew and repeat your analysis if required. So in summary, Adsec deals with both ultimate limits and serviceability limit state checks. The section I showed you there was a very simple rectangular section. It can deal with very complicated sections as well. It's a fully non-linear crack section check, and as part of that, it can also give you crack widths to your design code as well to make sure everything is within limits. I mentioned as well that Frew does as horizontal stability of the retaining wall. If you want to check the overall stability, then you can use our program Slope. Now, Slope, as you might imagine, is a slip circle analysis, which is designed for slope stabilities, and it will give you the various factors of safety for slippages. It works by the methods of slices, and there's various options in there, Swedish Bishop and Jambu in particular. You can also put in reinforcements, and if I call up an example from earlier, now here we have the retaining wall, the Frew model retaining wall, and the strut I put in as a ground anchor as a reinforcement. These are soil stratas, so I haven't modelled the wall itself. I've modelled the escarpment of the wall, and then for the toe of the wall, I've put in the slip surfaces a common point. So this common point is at the base of the wall, the toe of the wall, and so I'm going to say all slip circles will pass through this because by inspection, that's where the worst cases will be for our particular case. And we've got the grid for doing those checks. So let's run this analysis and see how stable our wall is. Now, in this particular case, with this toe embedment, we're getting a factor of safety of 1.2, which is possibly a bit low. So with this sort of information, we can adjust the toe depth to improve things. We can also refine the grid, the search grid around this area, so we can look in more detail at the problem. Alternatively, we can also look at other construction loads and see how much it can take. Now, that is a cantilever wall. We can similarly model gravity walls as well. And in this particular case, I've modelled the the retaining wall as an equivalent soil, but to make sure that again the slip circle doesn't pass through the concrete, which would be silly, we have a common point at the back of the wall here, and again we can analyze this, and we can see for this particular case I'm getting a factor of safety of just under 1.4 for these given ground conditions, backspan of the retaining wall, plant load, and so on. So slope. So it's a slip stability check. I mean, I was looking at circular slips. You can also specify your slip surface. It's good for slopes, embankments, and retaining walls. You can include anchors and reinforcements into that, and its main output is this factor of safety for stability. And at that point, I will hand over to Zina.
Thank you, Peter.
Who will take us on further.
Okay. Hello everyone. I'm going to be outlining how ExeDisp and SAFE can be used for retaining wall design. So we'll start off with ExeDisp. ExeDisp calculates displacements caused by excavations, including combined excavations. If you have a look at this picture in the corner here, you can just about see that as opposed to the excavation of one cube, we've combined a number of cubes. Also tunnels and shafts. But for retaining wall design, excavations is the most interesting thing. Now, the movements that are calculated at the surface feeds into a building damage assessment. Now, but basically Berlin's building damage categories have been built into ExeDisp. So ExeDisp produces an interaction chart and a table. Now, the interaction chart is shown in this corner here. And what the interaction chart tells you is the risk of your retaining wall to surrounding structures. So you've given information about where the structure is and its height and details about it. And on the basis of that, you can assess your retaining wall's risk. Now, ExeDisp considers a 3D problem and produces a 3D output, so it's a really useful tool for presenting results to clients. And for these reasons, it's been used extensively on projects such as Crossrail. So we'll now go into the analysis process for ExeDisp. Well, I've previously touched upon this, but ExeDisp models each excavation as a cube, and you combine these cubes to model more complex problems. ExeDisp calculates the surface displacement curves from Series C580. So this is the guidance for the design of embedded retaining walls, and it basically gives curves derived from ground movements measured during the installation of piles and excavations. Now these reflect the soil and stiffness type, and I've just given an example here of two curves in ExeDisp. Initially, for example, you install the wall, and the top graph here shows, if I follow this over here, this is actually from ExeDisp, but it shows a graph from Series C580, which is used as a lookup table. Then you get movement from the excavation of the wall, and the bottom graph here shows the Series C580 curve, which is again used as a lookup. So ExeDisp has been developed based on its use, so it's been developed in conjunction with engineers in light of challenges faced on a number of jobs, Crossrail being one of them. For example, ExeDisp considers the impact of corner stiffening. So initially, if you look at this, you can see that the corners, the displacements at the surface just radiate out. But in reality, that's not what happens, and there is a stiffening effect. And if you just look at the bottom graph, you can see the impact of the stiffening is now considered. And this is based on empirical calculations from Fuentes and Devrand. I've just put the reference at the bottom here. Another thing that's new in ExeDisp is, and this is much more significant to embedded retaining wall design, is that it more accurately models subsurface movements. So initially, as I previously mentioned, ExeDisp calculates the surface movements based on the curves given from empirical design. And at the base, it assumes that there is zero movement. So it's just an extrapolation from the top to the bottom. But in reality, the soil does move around the base. And the new feature allows us to define a subsurface curve. And this basically, in brief, gives us more detailed information about what happens at the base. So if you compare this top diagram here to this bottom diagram here, at the base you can see that there is movement, and that movement is modeled. Now we will be covering how to model a subsurface curve in an upcoming webinar, but in brief there are two ways you would model it. One way to model it would be to use a 2D plane strain finite element analysis with programs such as SAFE, where you model displacements around a retaining wall in your specific stratigraphy, and you cut and paste the results into our curve input here, and that could be used in conjunction with or separately to site data. So you could use inclinometer data to create a curve, and you can validate it using finite element analysis. Alternatively, you could either use finite element analysis or you could use site data. Now the benefits of this kind of update is it gives you more realistic subsurface movements. And once you've considered numerous amount of excavations, there's actually quite a complex analysis that ExeDisp does for you in a fairly simplistic way. So the best way to understand ExeDisp is to actually look at how it works. So I'm just going to send you into an example here. So initially you want to tell the computer what kind of, or the program, what kind of problem you're analyzing, and we're looking at embedded wall excavations. So I'm actually interested in displacement along a grid, but you can choose a specific point of interest to you or a line, and you can choose where you want that line to be so that you can have a look at specific buildings or utilities, for example, and the displacements along it. Now, then you have to put in information about your type of excavation. Now, I've defined a square excavation here, and I've given it a ground movement curve. Now, this is a subsurface curve that I've touched upon, but you can actually choose a surface curve. So, seeing that we're interested in subsurface movements, this is appropriate for us. But say we wanted to look at the surface movements of an excavation, we would use one of the excavation curves. Or we want to look at the impact of an installation of our wall, we would use the installation curve. So moving on, we'll have a look at the kind of curves that you can produce. Now I've previously mentioned this, but if we have a look, we can see that this is a Syria curve for the installation of a planar diaphragm wall. So you can actually have a look at your curve and check the movements and see that they're realistic for your problem. But I'm going to go into the subsurface curve. Now, this subsurface curve was created, it's just an example file, but it was created from a deep basement problem in London where we used a finite element analysis to produce the subsurface curve, and we validated this with field data. So it produces a curve, something akin to this. And this is basically an output of the finite element analysis, which has been input into ExeDisp. So we'll now have a look at the actual output. So this is my grid, this rectangle here, and along this grid you can see the movements and the displacements, and at the base you can see that the displacements aren't zero, they're about 8 to 10 millimeters. So this gives us very good information. So for example, if you had some kind of utility here, or you were interested in the kind of movements that were happening just below, not underneath, but underneath, not directly underneath your shaft or excavation, but below and around it, then this would give you good information as to what's happening. Excuse me, sorry. So, in summary, ExeDisp is a quick and visual tool to communicate movements from your retaining wall design. It also is able to carry out building damage assessments. So it's very useful to communicate to your clients and also to external parties. And our hope is to cover ExeDisp in more detail in an upcoming webinar. But I hope that was useful, and we're now moving on to one of our more comprehensive pieces of software, which is SAFE. Now SAFE is a 2D finite element analysis program. It's been designed by geotechnical engineers for geotechnical engineers, and it basically carries out a range of analysis to produce soil stresses and deformations and carry out hydrogeological analysis of soils. So SAFE is a more involved analysis than Frew or Slope or ExeDisp. So it would be used when empirical and limited equilibrium methods such as Frew are not adequate. And it involves complex geometry. So for example, if you had a more complex problem, you could use SAFE. And if you're interested in particular outputs such as groundwater flow, you could use a program like SAFE. So why would we use SAFE? Well, it deals with pore pressures and effective stresses separately. It considers gravitational load and initial stresses. It computes steady-state groundwater flow, and time-dependent consolidation is calculated as well. And it allows for a number of soil models, so it's not just a linear elastic model. It'll allow for models like brick and cam clay. So whereas something like Frew might produce something much more conservative, SAFE will model the soil in a closer manner so that you could get results which are less conservative. So the best way to understand the capabilities of SAFE is to look at an example. So here's one I prepared earlier. Now, SAFE includes auto meshing, and you're able to refine your mesh. So this is an example of the installation of a wall. This is initial run, and I'm just going to quickly pass through the mesh just to show you the kind of features that SAFE has. So as you can see, we can excavate, we can have the wall in there. We can excavate further, we can add UDLs, we can put props in, we can look at long-term consolidation, we can attach here these blue dots show a piezometric surface. So all these things are possible in SAFE, and I touched upon this previously, but we can also have a look at the materials. And as you can see here, it's been modeled as an elastic Moore Coulomb material, but as I've previously mentioned, you can model cam clay, you can model brick. So all those options are there for you within SAFE. So once we've created our mesh, we can actually run the analysis, and I'm just going to go into the graphical view now. And here you can see through the vectors, we can actually have a look at the displacement. But as I previously mentioned, SAFE also models factors such as seepage. So you can look at seepage and consolidation around your retaining wall. You can actually get the numbers out as well, and have a look at, if you're interested in a specific area, as to the amount of seepage that occurs. And SAFE has a number of outputs, so you can have a look at fill contours as well. If I zoom out, if you have a look at this column here, you can see that SAFE has a visual representation of a lot of different outputs. So we've got displacement, we've got total stress, effective stress, pore pressure, strain and seepage velocity. So there are a number of outputs that SAFE can give you to give you a more detailed view of your analysis. So if I just go from the start, we can just have a look at how displacement changes through the problem. Just have a better understanding of the kind of things that SAFE can do for us. Another useful factor for retaining wall design that SAFE can do is that if we take a section through our retaining wall, we can actually find values such as bending moment and shear force all through all the different runs that you produce. So it gives you very good information about what's happening inside the retaining wall. So I've only touched upon what SAFE can do, but it is a very powerful tool, and details of how to set up measures in SAFE and how to do the analysis will be covered in future webinars. So I'd really like to now thank you for your interest, and just ask if you have any questions to ask, please feel free to ask us. So I'm going to pass on to Nigel now.